Here's a video on how to tackle this particular example. Remember, we were finding area under the curve over a specific interval, and that was from, let's check it out, -2 to +2. All right. So over the interval, -2 to 2. That's what we're playing with this with. And we said that we need a sign diagram for this so we can figure out where the function's positive, where the function's negative. There's a bunch of ways to go about this. You might just be able to directly find the zeros. If you're a little uncertain, consider where sine of x is equal to 0. You don't have to do this stuff in pink, but if that helps you, I'd say go for it. Sine x is equal to 0 when we're talking about essentially multiples of pi, right? Here's your sine function. So when we're at 0, when we're at pi, when we're at 2 pi, 3 pi, 4 pi, so on, any multiple of pi, that means if x is any multiple of pi, sine of x is equal to 0. So the ... means so on and so forth. It's officially called an ellipsis. But yeah, so on and so forth, the left direction, could be -3 pi, -2 pi, could be -pi, 0, pi, 2 pi, 3 pi, so on, so forth. Again, you don't have to write that step, but if it helps you, I would say go for it. Now, if we're looking at sine of pi x, note that this causes a compression on the graph by a factor of pi. So any x values that existed on the graph of y equals sine x are going to turn into whatever those are divided by pi, which means that these happen when you're at -3, -2, -1, 0, 1, 2, 3, so on, so forth. So for us and our sign diagram, we're going from -2 to +2, which just means that -1, 0, and 1 are our other critical values, nothing else. And g of x is 0 for all of those. Yeah, I didn't factor in the 4, but 4 is a vertical transformation on the function. It's not going to affect our x values, at least not as a multiplier. Doesn't affect our intercepts in that way. So, is the graph positive? Is the graph negative? Chunk ton of ways to figure this out. If you want, you can kind of pseudo draw the sine function here. Woo! It's pretty much doing that. I know it's not 100% accurate, but it gives us that idea. And again, if it helps you, yeah, draw it. Why not? So we can see we're positive from 0 to 1, negative after that. We're also negative from -1 to 0, and positive from -2 to -1. That's probably the easiest way to get that sign diagram, is just picture the function. You know the sine function bounces up and down, so plug that in. Again, anything in pink, not necessary, but can help. So we want the area, and we can't just straight up say we're going to go from -2 to 2 for this particular function, because that's going to give us 0. And you can test out in the Desmos integral calculator if you want. But this area up top is going to cancel out this area underneath. And then this other area up top is going to cancel out this other area underneath, because we recognize that areas below, or integrals where the function is below the x-axis, are going to give us negative values. So this would be wrong. You can't write that when you're finding the area here. Remember, we are breaking this into chunks. So we're going to find the area from -2 to 1 of f of x exactly as it is. Not f of x, it's g of x. And we're going to subtract the area, or the integral value, from -1 to 0. Because its integral value would be negative, so subtraction for that. We'll add from 0 to 1, and we'll subtract from 1 to 2. Again, because that one would have been negative otherwise, so we count for it that way. You could do the step where you write absolute values instead, but this is just a little bit faster. All right. So we're doing all these things. This is for 4 sine of pi x. And that's 4 sine pi x for all of them. Computing all these integrals, you can do it a bunch of ways, but we do at some point need to figure out the antiderivative of 4 sine pi x. We know if we took the derivative of cos x, we would get negative sine of x. So that kind of gets us on a track. If we take derivative of negative cos x, we're going to get positive sine x. Okay, it's a little bit closer. If we take the derivative of cos of pi x, we're going to get sine of pi x, but because of chain rule, times pi. So if we take the derivative of negative cos pi x over pi, we'll get sine of pi x times pi over pi, and those will cancel each other out. So we're now a little bit closer, and we just need that 4 in there as well. So throw a 4 in front. Boom diata. This thing's done. All right. So that's what I'm going to put in for next steps. The area is what we get when we take negative 4 over pi cos of pi x from -2 to -1. And we subtract that same expression, 4 over pi cos of pi x, but from -1 to 0, adding that same expression, -4 over pi cos of pi x from 0 to 1, and subtracting that same expression, -4 over pi cos of pi x from 1 to 2. And now computing each of those, which might require multiple lines. All right. First one is going to have -4 over pi cos of x is -1, so cos of negative pi, minus -4 over pi cos of pi times -2 is -2 pi. That's the first one. So this is this. Next up, that one. Negative 4 over pi cos of pi x, the top value is 0, minus negative 4 over pi cos of negative pi. That's the yellow one accounted for. And so same for the rest of these. Plus negative 4 over pi, cos of pi times 1 minus negative 4 over pi cos of pi times 0. Orange. And then that reddish one. We're going to subtract negative 4 over pi cos of pi times 2 minus negative 4 over pi cos of pi times 1. And there's that. So those underlines in there just to kind of help see what's what. It's organization is going to be your friend here, and really just keeping track of each individual piece. You might even want to go to a scrap paper, write down what this one is, write down what this next one is, write down what this third one is, write down what this fourth one is, in terms of their larger expressions, and then piece them together on your actual work paper. Let's work this out. Oh, I did use the whole page. Look at that. There might be some things that cancel out. It is worth looking at. Cosine of multiples of pi is always either 1 or negative 1. So we can use that to fill things in here if we want. Are there things we can cancel out here? Not immediately seeing it. So let's just work it out. Cos of negative pi is negative 1, if I'm not mistaken. So if this is negative 1, then that whole value is 4 over pi. Cos of negative 2 pi is positive 1. So these positives canceling out, we get, for that one, 4 over pi. We're going to subtract whatever's in this next one. Cosine of 0 is, how you say, 1. So we've got negative 4 over pi. And then, let's account for this first. Cos of negative pi, we said was negative 1. So negative 1 times negative 4 over pi is positive 4 over pi times negative 1. So negative 4 over, pi. One thing super worth noting about the rest of these sums, as you're computing them, there's a lot of similarity. Right? We have 4 pi plus 4 pi. If we distribute this negative, this also becomes not 4 pi plus 4 pi, 4 over pi plus 4 over pi. And because of the symmetry of sinusoidal functions, you are going to notice that every one of those 4 areas that we're finding, right, we were looking at the area under sine x, or a transformation of sine x. And all these top areas are going to be equal to these bottom areas. And it's just 4 of the same area. And if you do happen to spot that, you do have to mention it's because of the the symmetry of sinusoidal functions, but it's just essentially 4 of these. And you can write, like you can ignore this other stuff and just say you've got 4 of those. That's totally valid. But since we're going through this long way, we're just gonna do it. This one's gonna work out to the same as the very first one. Oops. 4 over pi plus 4 over pi. And then the last one's going to work out to the same as the second one. Negative 4 over pi minus 4 over pi. If you do simplify, again, easiest way to simplify without calculator is to recognize that each one of these is the exact same value. So find out the value of one of them and then just multiply by 4. 4 over pi plus 4 over pi is 8 over pi. And we've got 4 of those. So our total area is, oopsie daisies, 32 over pi. The end. That was fun. Well, gonna stop the video now. Bye. Oh, there it is. Here he goes.